take a second until it just finds the HDMI. Yes.
Okay. Many thanks for organizing. Thanks for inviting me and the possibility to give this talk. Well, let me briefly say what is XOX. So XOX, the way to mark the nuclear diagrams, what was taught today, that's OX or in the first or second lecture, that's conformal geometry, right? And
It looks like OXO.
that's OXO. That's precisely. That's just step to the side. Right. I just because I don't explain this, so let me just briefly draw things in terms of matrices. So that's parabolic, which actually indicates a type of S3 and SP2. And actually sometimes things are confusing because the same can be written as D3. Right? And then this crosses first actually. That's kind of P1A. And if you draw it, that's corresponding parabolic. Okay, that's conformal geometry, so what I will be talking about, it's actually this. In a cell language, it is this. And in D language, so that's D, sorry. It's actually this. No. Like this. Okay, so we talk of geometries of type. Okay, so it's type H3 mod P13A, which means, as in lecture by Boris Kruglikov, that the model is actually quotient, the generalized manifold of this type, and there are several curvatures and torsions. So this one, as I said, was standard example, is conformal, but this is known somehow as, for example, Gendrian contact structure. But the same is not to be Legendre contact structure. It's actually usually assumes that torsion is zero, and people study curvature, and that's basically what Misha was trying to tell us about the curvature, because actually the in other real form is precisely CR in dimension 5, for example. And that's what Misha was trying to tell us, something like coefficients which you cannot hear. Okay? However, in my talk, actually, it will be different. So the curvature is going to be zero, and the important part will be torsion. Okay? And the reason for this is actually that it has relation to, well, to integrable systems. That's what I would like to tell you. Okay, this is, I will give some summary of previous work with Jennifer Aponte and David Calderbank, and then I will tell about current work joint with Omid Makmali. Okay, so I have to do some brief brief discussion of Jets formalism because I will need it. So I consider manifold M and space of Jets of functions of it. Okay, so I don't want to describe what they are, I'll just introduce coordinates. So coordinates on M will be X, and coordinates on jet spaces will be X and U alpha, where alpha is multi-index, and you may think of those as derivatives, but actually of course they derivatives only when you choose some sections. Okay, and then there's natural projection where you forget L's jets and you go to L minus 1 jets, and the important point here is affine bundle model on this vector space. Okay, so L's order symmetric polynomial on tangent bundle. In particular, when we consider projection from 2 jets to 1 jets, you observe quadrics here. So that's actually important point here. Okay, so fiber consists of quadrics on tangent bundle. Okay, if you take nonlinear differential, well, nonlinear in general differential operator, which is just functions of L jets, so its locus is geometrically PDE. And we consider this prolongation, basically including all differential corollaries. So we compose it from the left with total derivative operations, or simply just differentiate the equations. Okay, then we get locus in equations, that's prolonged equation. Now, if it takes this function f, I take this differential, okay, it's going to be one form on jet space, and then I restrict it to vertical fiber. Now, here actually that's a fine structure. Okay, so get polynomial of degree L on this cotangent bundle. Well, lift to jets. And why I need to lift to jets? Because whenever I differentiate, there will be coefficients depending on jets. Okay, and this is called symbol. So, like computationally, it looks like this. Well, here I take only the top parts, like summation by multi-indices of degree L. Okay, that's the coefficients. They depend on jet. Well, unless the operator is just linear. And that's actually symmetric L vectors. Okay, so we get symmetric L vectors with coefficients actually depending on jets because that's pullback bundle. Okay, and important that we talk about equation, not particular differential operator, but it's about locus. This equal to 0. So I can change f equal to 0 to whatever with the same thing. I can multiply by non-zero functions. And of course, this object is not invariant, however, it's conformally invariant. Okay, so it's conformal class of these L symmetric tensors that plays a role. Okay, so this can be generalized, I started with functions, so okay, that's scalar differential equations, but can be generalized to system of PDEs in the same way. Okay, so for an operator of second order, that's kind of main example, but the series is larger. So we have the following. So the symbol, that second order thing will be, okay, that's symmetric by vector, and that's coefficients. Okay, minor reminder that the summation I less than or equals than j. If you would like to write the matrix, you have to remember that non-diagonal terms have to be split, so there's division by 2 here. Okay, but that's kind of standard school story, how to write matrix operator. Okay, so we get a quadric. This actually defined what was called characteristic variety in geometry of PDEs, in gas dynamics and fluid dynamics that people call dispersionless relations and so forth. Okay, so we assume that this characteristic variety is, well, it's quadratic because second order. We assume it is actually non-degenerate. So the matrix, well, has non-zero determinant. In this case, we can invert the matrix. Okay, so it was matrix of symmetric by vector. Non-degenerate give us matrix of symmetric form. This one. Everything up to scale, right? So it's conformal. Okay. So here I say it's symmetric by linear form on Tx and U. And what is U? U is actually this background solution. When I did computing symbol and other stuff, so everywhere there's some U standing. What is this U? Well, this U is solution to this equation. In fact, well, usually it's very difficult to solve nonlinear equations, so I, of course, cannot have control over all possible solutions. But in all my calculus, I just need some finite number of jets, like 2 jets, 3 jets with prolongation and so forth. So this is just algebra. That's easy to operate. Okay, so I understand that actually I have my manifold, base, and the solution. So basically, like mu is manifold plus solution. Or I can use this u to lift my manifold into, well, trivial or non-trivial bundle, and then prolong it to infinite jets. So in principle, I can understand this as solution viewed as submanifolds in here. Okay, and now we have this conformal structure of this thing. And that's kind of this the base for geometric approach to integrability. So in my first paper with Eugene Ferapontov, that actually we read off all integrability features from such conformal structure. Okay, here's an example. That's f equal to 0 gives locus which is called DKP, dispersionless Kedemtsev-Patviashvili equation. You see it's slightly non-linear, right? So there's non-linearity sitting here, that's linear terms. Whenever we do linearization first, right? So we perturb u, differentiate by perturbation, we get these operators, second order operators, fine. So this gives just dt dx, this gives just dy square, and these things gives 3 terms. Okay? So, well, when you, so computation. And you see that actually this operator depends on u, right? Well, here's u, here's u, here's u, well, it's actually jet of u. That's background solution. So we know something about it. Okay, when I talk about symbol, I drop off lower order terms. This is gone. This is 0 order terms gone. So only second order terms remain. Here it is. So still depends on background solution. Okay, that's matrix of this thing. Right? So you see this off term, off diagonal terms give 1/2, of course. Right, and then I invert, I get this thing, and I write the corresponding metric, which is defined up to scale, so conformal structure. And also this gives me equation for twisting variety. Okay, so that's the...
Sorry, I have a question. So I didn't understand the notation, so LF is
linearization, right?
Is the fiber, when you project from second to first, is it?
Well, linearization is something that we kind of learn in school. It's absolutely the same, right? So when we teach differential equations to students, right? So we need operator near singular points, but its equation, well, solution is something which makes things 0, right? So linearization of operator f on solution u is what? F of u plus epsilon v minus f of u, actually 0 if u is solution, well, divided by epsilon, so it's linearization on v. Okay, here I have to take limit epsilon goes to 0 as usual. Yeah, that's linearization. Right?
And by integrability?
Yeah, I have to say, I'm not yet there. Okay. So the integrability, there's at least 2 different things, and in particular as today what means Cartan integrability, or integrable system and so forth. There's always some 0 curvature condition. But it can be solitonic type, or it can be dispersionless type. I will be talking about dispersionless type. Okay, I'll specify. Okay, so I'm starting here with specification. It's maybe quite abstract, but actually that's what people in mass physics mean, and actually for this audience it should be easier. That's what they expose. So we have this mu, manifold Swiss function. We consider it's actually a bundle with fiber P1 over it. Okay, so you can work in real category, in complex category, depending on this you understand what P1 is. And a dispersionless Lux pair is such a rank 2 distribution here in P1 bundle, such that, first of all, this thing depends only on finite jet, that's so-called locality, no integrals, no like d-1 operators. So it depends only on finite jet of this u which appears in here. And second, that this distribution is transversal to fibers of this bundle. Okay, which means that I have some x and y which are not quite vector fields in here, because they're actually sections of tangent bundle of Tm pulled back in here. In other words, they can depend on lambda. Those things. The lambda-dependent vector fields, where lambda is actually coordinate on this P1. And, okay, so plus this. Plus something to lift. And certain most important that this rank 2 distribution actually is Frobenius integrable on equation. So as physicists say, on shell. So if I assume f equal to 0, then I can derive this differential constraint, some number of equations, from f equal to 0. And only finite number of objects involved, so it against some algebra. So geometrically we have the following picture. So if this is n-dimensional, right, the P1 bundle because some second plus 1 dimensional. Here we have rank 2 distribution, Frobenius integrable, if this satisfies the equation. So I can actually consider local leaf space, boom, minus 2 dimensions. So that's called twistor space. Okay, so then we call this pi, which is projection of pi hat, two-plane congruence. So basically it's spanned by these two vector fields x and y, but they're not vector fields because they actually depend on lambda. That's called in physical usage spectral parameter. Okay, so basically if you vary lambda, it's we get one parametric family of two planes at every point. Okay, we call it two-plane congruence. Some people say that we have to use the word pencil, but there's also reason for congruence. Okay, so and here's a theorem which we proved with David Calderbank. Well, somewhere there. That a dispersionless Lux pair must be characteristic, which means that for every solution, okay, and every point and so forth. So if you take this pi of x, this two-plane which depends on lambda actually, right, and take any annihilator of it, okay, that's two-plane consists would generate a span of two vectors. We take covector which vanishes of this. There are many such, okay, and any such actually belongs to characteristic variety. So if I compute symbol of it, okay, if sigma is quadric, right, so I have to put two thetas there. If sigma is cubic, I have to put three thetas. Just polynomial computer does this, right? Okay, that's very strong condition actually. Well, just geometrically, what's written is there, it says that there's coisotropic to plane for the conformal structure we discussed. But usually in geometric configurations, we would like to discuss conformal structure which are non-degenerate, which have representative metric, right? And coisotropic to plane usually don't exist in higher dimensions. They actually exist in dimension 3 and dimension 4. Well, kind of trivial in dimension 2. Okay, in dimension 2 the condition is vacuous. For dimension 3 coisotropic to plane, it means it's just degenerate plane, tangent to cone. Well, okay, I have to assume here some signature. Okay, so Lorentzian signature, Wilcox-Riemannian signature, or everything complex. And then the space of such planes is just 1p1. Okay, rational conic. For d equal to 3, they have to be totally null plane. Restriction of metric is 0, and there are actually a space of such two planes. There's two p1s. One called kind of alpha planes, other called beta planes. Alpha and beta convention, if you change orientation on manifold, they swap together. Okay? So, if n is greater than 4, then equations with non-degenerate quadratic symbol cannot be integrable, cannot be dispersionless integrable. And this kind of was, well, discussed in mathematical physics community because like all examples they knew they were having a degenerate symbol, but that was the explanation actually. Okay, so let me give, what do you have in terms of time?
So you are somewhere in the half.
In the half, right? Okay. So let me briefly discuss two integrable background geometries which you know before. So dimension 3 is Einstein-Weil. That was already kind of discussed today. So we have conformal structure, And actually we look for conformal connection. It was called conformal connection today. So something to preserve conformal class. For representative metric, it means when you differentiate, you get something proportional to metric. Coefficient of proportionality is one form. Okay, you can in principle just start with one form and representative metric, and that can read off the connection D. Okay, so that's called wild structure, this story. And if we have this, then we can compute Ricci tensor of this connection. Its skew-symmetric part is proportional to d omega. It's not the interesting part, but symmetric part is interesting. And if we write the equation as proportional to g, that's two tensor, that's some function, not constant, but in general function, then that's actually a constraint called Einstein-Well condition. Here's an example. You can see the same example as before. DKP, that the metric was derived there. Omega must have this form. That's a computation. There's some magical formula which actually gives a way to compute. Okay? And then actually it is Einstein-Well. So this structure is Einstein-Well provided U is a solution. So we get as many Einstein-Well structure as actually we have solutions of this. And this is integrable equation. It has a lot of explicit solutions. Okay, and Lux pair, it's given by these two vector fields. So you see lambda dependent part on the base, and that's left to configuration space. Okay, and this thing gives integrable distributions. This Frobenius theorem calls for the corresponding vector distribution. Okay, so in dimension 4, the corresponding equations is self-duality equation. So if you take wild tensor of conformal structure in dimension 4, okay, then we compute half of it, plus or minus depending on some choice of alpha and beta. Okay, and then we compute star, and yeah, so we compute star, we compute this plus minus thing, and then part of it is 0. For example, W minus is 0, then we get self-dual structure. But okay, this locally here doesn't matter actually, self-dual, anti-self-dual. An example is second Flebansky equation. That's this kind of thing. Again, you see second order. Therefore, when you compute symbol, it's symmetric bilinear tensor, inverted, get such a metric, and yes, it is actually self-dual on any solution of this. Okay. Well, it's not metric, actually conformal class. That's choice of representative is actually very good because it actually turns out to be Ricci flat, also modular this, but it's kind of besides what I'm discussing here. So there's the background actually good equation. It's that half of wild tensor is 0, say self-duality equation. Okay, so high dimensions. So in high dimensions, as discussed before, it's not possible to get any conformal structure. So what do we get? What kind of geometry is there? And good actually system to consider are second order and some systems and so forth. But okay, so let's discuss second order ODE, so quadratic symbol. Okay, then maximal rank of this is 4 as a corollary of theorem by David Calder-Bank and myself. So what do we have? So we can do actually contraction of this guy and cotangent space. Okay, then we get subspace here in tangent space, right? So if you contract these two things, okay, so one of the index is killed, but okay, so we just evaluate sigma f on all possible covectors. So we get subspace here at every point. So that's a distribution. This distribution has rank actually the same as sigma, so actually as not greater than 4. And in general, just non holonomic, and in general, rank is equal to 4, generic solution. So that's what I will assume. Okay, so then we actually can restrict, and we have this vector on this distribution, and then on this distribution we can invert it. We cannot invert it actually on the entire tangent bundle, right? It's but we can actually invert it here. So then we actually get a metric defined up to scale on this distribution. So it's subconformal structure. Okay, so which non-holonomic distribution arising here? That's still a question. Majority of those don't satisfy the condition for existence of dispersionless pair already on the level of symbols. Okay? In other words, they cannot be integrable background geometry. In this talk, we would like to concentrate on dimension 5. Okay, so what do we have in dimension 5? Okay, delta is non-formal distribution. For genericity condition, we assume is contact. Okay, simultaneously, on this contact structure, we have a conformal metric. So, also, with contact condition, of course, we have conformal symplectic form. Therefore, we have operator. We can divide one by the other. We can normalize this operator by norm equal to 1. Okay, and then this conformal structure is compatible if we take the corresponding metric right here, it's just at one point, and then there's two families of null to planes, as we discussed before. Alpha and beta, let's concentrate on alpha, for example, self-dual part, and we want them to be simultaneously, they're null with respect to G, but we want them to be null also with respect to omega. Okay, there has to be Lagrangian. Okay, if we have this for alpha, then actually it cannot hold for all beta. And can hold for some of those, at most for two particular, from one parametric family. Okay, and that's the way actually we can choose alpha or beta. In 4 dimensions, we actually don't know a priori what is alpha, what is beta. We have to go and compute the integrability conditions. Here we can decide it on the level of algebra. Okay, compatibility is equivalent to this condition. Okay, J square is equal to 1 or minus 1. Okay, trace is 0. So it's either actually CR or para-CR structure. Like if delta is equal to plus 1, it's para-CR structure, then actually J square equal to 1, and we have that tangent, that delta is split into sum of two distributions, L plus and L minus according to eigenvalue plus or minus 1. Okay, and they are actually Lagrangian. There's symmetric theory of non-Jumper equations, also splitting of Lagrangian in 5D into 2 plus 2, but those actually are symplectic. So here they are Lagrangian. That's fine, but they are Lagrangian only as distributions. Okay, so we can check their corresponding integrability conditions as distributions. And in general, it doesn't hold. For delta equal to minus 1, well, the same story holds, but we have plus minus sign, and so it's almost CR structure. So it's almost Legendrian or Lagrangian contact structure and almost CR structure. That's what we're talking about here. Okay, there of course there's this remaining freedom which is G0, and it does reparameterization. Well, center doesn't act on this lambda, but SL2 makes projective reparameterization of P1 fiber. Okay, so maybe I skip this because that's more or less what I've drawn in here. That's corresponding grading. Okay, so that's minus 2, that's minus 1 here, it's 4-dimensional. So you can see that actually that's models our tangent space. That's 5 dimensions here, and that's like L minus, that's like L plus, and they break it to here, which is like normal direction. Okay, and that's structure group here. Now, if we just apply general theorem of parabolic geometry, because that's parabolic geometry, then the harmonic curvature splits into 3 parts, 2 torsions and 1 curvature. And well, in the case of para-CR, these come independent. In the case of CR, that's actually one irreducible piece. Okay, so we have this story. Okay, so let me now formulate in terms of those things what are the conditions for existence of dispersionless Lux pairs. So, and I recall 2 theorems in order to show like what kind of model we would like to get. So, a theorem with Saraponta with the integrability of equation with dynamic reductions is, I don't say what it is, but it's okay. So in 3D is equivalent to Einstein-Wild property for this conformal structure on any solution, on any background solution. For 4D is a duality property. Okay, so when dispersionless Lux pair exists, you have to solve some equation. That's kind of PD equation, but that's very algebraic. We just go and compute it, complete algorithmic. With David, we say that, well, this dispersion slash pair integrability, it's the same, so it's kind of in one direction that was strengthening of these, but not in the direction of quadratic integrability. Okay, so let's say this was more three-dimensional here, there's a bit more four-dimensional story in here, but this was about 3D and 4D. Okay, now with OMI, our theorem is that integrability, okay, the same story, is equivalent to zero curvature condition, where W is precisely this guy. Okay, so that's actually curvature, that's torsions, so we don't care about torsions, they can be arbitrary, but the condition is zero curvature precisely in terms of parabolic geometry things. Well, that's modular, so on shell, right, on any solution of PD. Okay, so example, that's five-dimensional equations. It generalizes Plebanski equation. So it, okay, if I have time, I'll show six-dimensional counterpart. So we compute its symbol. Okay, so it's actually visible to be of rank 4 because it's actually symmetric product of two vectors, right? Symmetric by vector, and these are the vectors which generated. Therefore, delta, the thing which contracts with covectors, generated by V1 to V4. Okay, or equivalently, it's annihilator of this one form, okay, which is generically contact. So we compute the corresponding metric representative for conformal structure, this one. Okay, we have this coordinate representation, and then we can compute alpha planes and beta planes, and alpha, well, we want actually this to be 0, right, on delta, so it's actually this condition and this condition in terms of exterior forms, or in terms of vector, it is this and this. Okay, and now it's easy to check that actually it works. That's the corresponding vector field on the base, and actually it has trivial lift. There's no d by d lambda story, right, as previously, because you see just lambda dependent vector fields on the base, not something like plus del lambda Jones here. Okay, so that's integrable story. Can we check it? I actually would like to advise how much time do I have?
About 6 minutes.
6 minutes, yeah. Okay, so maybe I will not go to... Actually, it's fine. I would like to say a couple of words about this. So we can write master equation which controls all possible zero curvatures of conformal structures. So all those subconformal geometries with zero curvature condition can be described by this. So here we just write what is W. So W actually has, it's quartic. So it depends on this parameter lambda. So I can decompose by parameter lambda, get quartic. And actually then we can write all possible zero curvatures of conformal structure in the following parameterization. So contact form Darboux and metric contains actually 4 functions, u, v, w, and z, and this depends on coordinates, which are x, y, p, q, r. So 5 coordinates, 4 dependent functions. Those functions satisfy PDEs of second order, those, and this choice actually automatically lets W4 equal to 0. Okay, so we have 4 known functions, 4 constraints of second order, easy computations. Of course, from Kovalevska's theorem, the general solution depends on 8 functions of 4 variables. And there's no big gauge groups. There's still small gauge group remain here, but it doesn't change this count. Okay, so yeah, so that's kind of story for those who like numeration. So Einstein equation for about equations 3D, 4 functions of 2 variables, self-duality in 4D, 6 functions of 3 variables. So here's 8 functions of 4 variables, and we don't know what's going on. Okay, but yeah, so it seems to come. Okay, so that's 3-star picture. So we are actually where we are. So we are here, right? So that's correspondence space. We can always lift up. We never can project to conformal story here, right? But actually, that's the 3-star direction here. So sometimes these things with zero curvature can be obtained from projective structure. That Omid was talking in his lecture about it, right? And well, this can be made quite precise. So here are things discussed. Okay, which I'd like to skip this. Okay, that's how things look for projective structure. But okay, let me just drop it. There's some twister story about 7-dimensional uniform degenerate CR. So again, I will skip this. So I briefly summarize the story. So the main difference with high-dimensional situation is that the metric has only one family. So like in 4 dimensions, there's alpha and beta, and you have to kind of correctly guess what is correct or compute, right? So here you see right away from algebra what they are. So that's one family. And yeah, only sporadic examples exist in 4D. So I don't discuss those. And what is important in higher dimensions, actually, all types algebraically special. So first of all, we get also algebraically special solution by prescribing symbols, but also the equations themselves are algebraically special. Right, so I'd like to tell, my last slide, I'd like to take something about this, because this conference about Cartan and parabolic geometry. So it's actually, there exist two things which resemble dimension 5, but in general there's theory in higher dimensions, but it's no longer parabolic. But there's two kind of exceptions. Okay, that's okay. I'll skip this. So here it is. So let's call parabolic geometry DLP compatible. That's dispersionless pair compatible background geometry, if it admits subconformal structure on distribution corresponding to G minus, and we have the full compatibility condition. So rank of this distribution is 3 or 4. That's coming from this theorem with David Vanderbank. And there exists G0 invariant conformal structure on this one. Okay, it turns out to be unique under this condition. And also there exists one parameter family of C null and also with isotropic with respect to bracket 2 planes in this. Okay, so it's simultaneously null with respect to this, and or degenerate with respect to this, and actually with respect to bracket from wedge to G minus 1 to G minus 2. Okay, and if we in addition have something like W equal to 0 for curvature, that will be called integrable background geometry. So then, actually, the list is very short. 3-dimensional, 3-dimensional conformal, 4-dimensional conformal. The one thing we discussed today, and 2 more things. But one of them is actually non-regular. So actually, this one is interesting in its own, but this one is not regular. So that kind of short story. Otherwise, there exist, of course, symbols which satisfy this. They will be Cartan, but not parabolic. Okay, thanks for your attention.
Thank you very much. Questions, comments? Rita?
Yes, so Boris, I always ask you the same question. So for the grading that you put, right, because you write Satake, I write Vogel diagram, so I have difficulty. Somehow it seems to me that for the families, there is somehow an obvious grading that you can take once you in the diagram. But for the exceptional, my work with Chua, we prove that there is more room than choosing the grading. Did you explore this direction?
First of all, you talk about superstore, right? Probably.
No.
Even about it? No. I mean, that's up to conjugation. Grading is the same as just parabolic, right? Yeah. I consider.
The question is, how many gradings can you pick?
As many as I can put crosses on those diagrams.
Yes, I'm telling you that for families, yes. But for exceptional, there are some extra ones you don't see. You need to put this phi root, the negative,
I tend to disagree now with you, but let's discuss afterwards. Of course, you cannot put crosses whenever you want, because you have to respect coloring of Satake diagram.
Yes.
For sure, yes. But still, it only depends on put crosses, right?
Sorry, can you just repeat what you said about B3, P13? Because, you have, if I just restrict to regular ones, those are in correspondence with B3, P3 geometries, which are...
Then there will be no alpha planes, right? So if
Is
you like
not-
alpha planes, we have to assume.
Okay, so
regular.
that curvature component gets turned off, but then
Yeah.
you're saying other non-regular components, those are the ones that control what's going on. Okay.
Well, yeah, it kind of will be flat, not interesting story, right? So we would like some variety of things.
But do you have any vibration over B3P1 a priori, or you need those components as well?
If I may answer a bit later, it would be nice. Yes, that's a good question, but I have currently forgotten.
Right, let me thank Boris again. Survive the